Now that we've defined a logarithmic function, we're going to graph a basic log function. To graph these by hand, we convert them to their exponential form. So let me show you an example of a basic log function. We have f of x equals log to the base 2 of x. Well, this is nothing more than y equals log to the base 2 of x, but this is equivalent to the exponential form of 2 to the y equals x. So to graph the function, we will substitute values for y and solve for x. So I have a table, and we're going to let y have the values -2, -1, 0, 1, and 2. When I input the value y into this expression, then 2 to the -2 is the value of x, which would be 1/2 squared, or 1/4. When we input -1, we get 2 to the -1, which is 1/2. 2 to the 0 is 1. 2 to the 1 is 2. And 2 squared is 4. So these numbers are probably ringing some bells, right? When we looked at the basic exponential function, those values of x and y were interchanged. And that's exactly what the log function is. Recall, it is the inverse of the basic exponential function. And so even think about, remember how we have to interchange the x and y, and on the basic exponential function, the y equals 0 is the horizontal asymptote. So when we think about interchanging x and y for the basic log function, we interchange x and y, so y now becomes x equals 0, and that is a vertical asymptote. So we can graph these by hand, and on the coordinate system we're going to plot, be really careful here, I have to plot 1/4, -2, right? 1/4, -2, 1/2, -1, 1, 0, 2, 1, and 4, 2. So we have this vertical asymptote at x equals 0. We have this key x-intercept point of 1, 0. Remember, on the basic exponential, that key point was 0, 1. So some key characteristics of the graph of f of x equals log to the base 2 of x. The domain is only 0 to infinity, right? We can only input positive values into the log function. But the range, since the graph extends infinitely down and up, the range is all real numbers, or -infinity to infinity. The x-intercept point is 1, 0. There is no y-intercept. It never crosses the y-axis. The vertical asymptote is the equation of the vertical line through 0, which is x equals 0. And this is a one-to-one function. And also notice that it is an increasing function. And so I move my finger on the graph from left to right. I am going up, 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 up. And what about the end behavior? So as x goes to 0 from the right, what part of the graph does that refer to? As x goes to 0 from the right means I'm coming into 0 from the right-hand side. But what's happening to the graph at that part? It's going down to infinity in the negative direction. So we would say y goes to -infinity. If we look at the behavior on the other side as x goes to infinity, well, in that case y is going to infinity, right? As we go to the right end of the graph is going up, which is going to infinity. So graphs of y equals log to the base 2 of x and y equals 2 to the x, because they are inverse functions, when we graph them on the same coordinate system, we find that they are symmetric about the line y equals x. So if I draw this diagonal line through 0, 0 with a slope of 1, that is my graph of y equals x. And if I flipped the two graphs across this line, fold my graph along that dotted line, I'll see that they are mirror images of each other. But also notice the relationship between the ordered pairs, right? If xy is on the graph of 1, then yx is on the graph of the other, right? We interchange the values x and y in the coordinates. So just to see these side by side, the domain of the log function we said was 0 to infinity, and notice that is the range of the exponential function. The range of the log function is all real numbers. The domain of the exponential function is all real numbers. The log function has a vertical asymptote at x equals 0. The exponential function has a horizontal asymptote at y equals 0. The log function passes through the key point of 1, 0, but the exponential function passes through the key point of 0, 1. Now we're going to look at what happens when the base of the log is between 0 and 1. So in this case, y is equal to log to the base 1/2 of x. Well, when we convert it to the exponential form, it is 1/2 to the y equals x. And we have a table of solutions, so we would do the same thing that we just did previously. We'll input the values of y, which are -2, -1, 0, 1, and 2. And when we input -2, 1/2 to the -2, remember with a negative exponent I have to take the reciprocal of my base. So this becomes 2 squared, or 4. 1/2 to the -1 is 2 to the 1, or 2. 1/2 to the 0 is 1. 1/2 to the 1 is 1/2. And 1/2 squared is 1/4. So in this case, I would be plotting the points 4, -2, 2, -1, 1, 0, 1/2, 1, and 1/4, 2. So when we plot those on the coordinate system, notice that we get this graph, that it is really the reflection across the x-axis of what we just had. So the domain is still 0 to infinity. The range is all real numbers, -infinity to infinity. The x-intercept has not changed, it's 1, 0. There is no y-intercept. The vertical asymptote is still at x equals 0. It is a 1-to-1 function because it passes the horizontal line test, but this time we have a decreasing function. And just like with the exponential, right? Do you remember if we had y equals b to the x when b was between 0 and 1? That graph was a decreasing exponential function. So when the base of the log is between 0 and 1, we also get a decreasing logarithmic function. As x goes to 0 from the right, so this time as we're going in from 0 to the right, notice that the graph is going up now. And so y is approaching positive infinity. If we want to look at the end behavior as x goes to infinity, then y is going to, well, the right end of the graph is going down, so we say it is going to negative infinity. So the graphs of y equals log to the base 1/2 of x and y equals 1/2 to the x are also inverses of one another. Their graphs are symmetric about the line y equals x as shown. So on the graph of the exponential function, 1/2 to the x, I have the points -2, 4, -1, 2, 0, 1, 1, 1/2, and 2, 1/4. But on the graph of the log to the base 1/2 of x, I have the points 4, -2, 2, -1, 1, 0, 1/2, 1, and 1/4, 2. So just like with exponential functions, the base of a log function determines its shape. If the base is greater than 1, the logarithmic function is an increasing function. If the base is between 0 and 1, the log function is a decreasing function. So I have a slide that has the graphs of both of those types of log functions summarized. So we see that based on the base, either being greater than 1 or less than 1. It's either increasing or decreasing, but all of those other components stay the same. The domain of log base b of x, regardless of what the base is from 0 to infinity. The range is all real numbers. The vertical asymptote is at x equals 0, and it passes through 1, 0. So what we're going to do now is to graph log functions using transformations. I didn't summarize those again here, but hopefully you have learned those throughout the course. We want to state the domain and range and identify any asymptotes. So on this first function, I have y is equal to log to the base 2 of x plus 3 plus 1. So it's really important for us to have in our mind what points are on the basic log to the base 2 of x. And we just did this a moment ago. But for instance, we talked about the log base 2 of 4 was 2. The log base 2 of 2 is 1. The log to the base 2 of 1 is 0. The log to the base 2 of 1/2 was -1. And the log to the base 2 of 1/4 was -2. So think about those key points. And then what we need to know is how does a log to the base 2 of x plus 3 plus 1 transform this basic shape? So remember that the plus 3 on the inside, that's an inside change. We'll shift the graph of log to the base 2 of x left 3 units. And plus 1 is on the outside, so it's going to change it by shifting it up 1 unit. So that means our point that was originally at 4, 2 is going to now move to shift it left 3, so down 1, 2, 3 to the left, and up 1. So that's going to move to the point 1, 3. This point of 2, 1 is going to move left 3, so left 1, 2, 3, up 1, which will take me to the point -1, 2. 1, 0 moved left 3 is 1, 2, 3, up 1, which is at the point -2, 1. 1/2, -1. If I go left 3, left 1, 2, 3, up 1, be at -2.5, 0. And the 1/4 -2, if I go left 3, 1, 2, 3, up 1, is at like -2.75, -1. Now I have to also think about my vertical asymptote. Remember we were originally at x equals 0, but if I shift this left 3, so left 1, 2, 3, and up 1 is not going to move it, so it's going to be at x equals -3. So I'm drawing a vertical line through x equals -3. And then we can connect the points of this new transformed log function, which are going to go through these points in an increasing manner. And so the domain of my transformed function is everything to the right of -3. So that would be from -3 to infinity. The range of this function, the graph extends infinitely from the bottom to the top, so the range is all real numbers, -infinity to infinity. The vertical asymptote is at x equals -3. And then just keep in mind that our key point of 1, 0 through that transformation was left 3 up 1, went to -2, 1. Now another way you can find the domain of these logarithmic functions is you want to set the argument to be greater than 0. Right? X plus 3 is greater than 0, so x has to be greater than -3. Now what about y is equal to negative log to the base 2 of x plus 4? So when we think about the transformations, what happens when we have a negative on the outside? So do you remember this is like taking the opposite of y, and the opposite of y occurs across the x-axis. So the negative on the outside is a reflection across the x-axis. And then plus 4 means that we're going to shift up 4 units. So the reflection across the x-axis will keep x the same, but it will take the opposite of the y value. And shifting up 4 units is going to add 4 to the y value. So remember, there is an order in which we need to do things. We need to do the reflection, right, the thing that impacts the x-axis. So reflect across the x-axis first, then shift up 4 units. So what points are we transforming? Well, if you remember that table of values that we just looked at, 4, 2, 2, 1, 1, 0, 1 half, negative 1, and 1 fourth, negative 2. So this is another one of those basic functions that you need to add to that list that we learned in section 11. You have the basic exponential now, also the basic log, and those are the last that we're going to cover in this course. So when I think about how do these transform, I'm going to put the original points in green on my graph. So I'm going to plot 4, 2, 2, 1, 1, 0, 1 half, negative 1, and 1 fourth, negative 2. So let's think about what the transformation would do. The 4, 2 in the reflection across the x-axis would actually become 4, negative 2, right? And then I've got to shift that up 4 units. So negative 2 plus 4 would take me to 4, 2. So actually that point stays where it is. That's not always the case, but it will actually stay there. Right, so I had to shift it over to 4, negative 2, and then I had to move it up 1, 2, 3, 4, which takes me back to the same point. 2, 1 to reflect across the x-axis would become 2, negative 1. And then I need to add 4 to the negative 1. So that would take me to the point 2, 3. Right, so 2, 1 goes to 2, negative 1, but then I go up 1, 2, 3, 4. 1, 0 through the reflection across the x stays at 1, 0. Then I need to increase the y value by 4, so 0 plus 4 would take me to the point 1, 4. One half, negative 1 would take me to 1 half 1 when it's reflected across the x-axis, and then I need to shift that up 4 when I add 4 to my y values. 1 plus 4, I get 5, so that transform point is 1 half 5. And then 1 fourth, negative 2. When I reflect it across the x, it's 1 fourth, positive 2. And then I need to shift that point up 4 units by adding 4 to my y value, so 2 plus 4. Takes me to the ordered pair 1 fourth, 6. What is our vertical asymptote? If I reflect this vertical line of x equals 0 across the x-axis, it stays at x equals 0. And if I shift it up 4 units, I'm not moving it anywhere left or right. So it will stay at x equals 0. And so I can draw the points now, and this graph will be a decreasing function as I come through all of those transformed points. The domain, so my vertical asymptote is x equals 0. The domain of the function is from 0 to infinity, and the range is negative infinity to infinity because the graph is extending downward and upward infinitely. Now the key point of 1, 0 through that transformation move me to the 0.14. This last one I want to do is f of x equals log to the base 2 of 3 minus x. And so here, I'm going to write this as log to the base 2 of negative x plus 3. Now, this transformation involves two things. We have a negative on the x. So remember, negative on the x means that we will take the opposite of x, which is a reflection across the y-axis. And then the plus 3 suggests that there's going to be a shifting left of 3 units. So again, we're going to think about our basic log function. So y equals log to the base 2 of x. And that was including the points, 4, 2, 2, 1, 1, 0, 1 half, negative 1, and 1/4, negative 2. So when I think about the order that I need to perform these transformations, I'm going to need to shift left and right and then reflect across the y-axis. Okay, so we do the x change and then the y-axis change. So I'm going to shift left 3 units, so the 0.41 would subtract 3 from the x value to become really 1, 2. But then to reflect that across the y-axis, so if I shift left 1, 2, 3 to 1, 2, reflected across the y-axis would become negative 1, 2. 2, 1, I'm going to shift left 3, so 2 minus 3, 1, would be at negative 1, 1. Right, so shifting left 3, but then I have to reflect it across the y to become 1, 1. So the reflection across the y is taking the opposite of the x. So 1, 0 through this transformation would become 1 minus 3, 0, or negative 2, 0. But then when reflected across the y-axis becomes 2, 0. 1 half, negative 1 would move to 1 half minus 3, negative 1. 1 half minus 3, we'll just say it's negative 2.5, negative 1. And when we reflect that, it would be a positive 2.5, negative 1. And then 1/4 minus 3, negative 2 would become negative 2.75, negative 2. And then reflected takes me to 2.75, negative 2. And then what about the vertical asymptote? Right, originally my vertical asymptote is at x equals 0. When I shift it left 3, it becomes x equals 0 minus 3, or x equals negative 3. But then when I reflect that across the y-axis, it becomes x equals 3. So there is a vertical asymptote at 3 through the x-axis. And so I can draw the graph through these points. And so what about the domain and range? The domain is now everything to the left of 3, so that would be negative infinity to 3 with the parentheses. The range is all real numbers since the graph extends infinitely up and down. Notice our key point of 1, 0 transformed to 2, 0. And the graph is now a decreasing function. Now again, another way you can think about the domain, negative x plus 3, or 3 minus x, however you want to write it, has to be greater than 0, which means that negative x has to be greater than negative 3, and when we divide by negative 1, we get that x is less than 3. So that can also help you check your work.